What are RAGs? How can you integrate RAGs in existing pipelines? And how can you use Qwen 2.5 72B for your generative needs? In today's video, we will try to answer all these questions. So join me as I guide you how to implement a RAG pipeline using simplified Boolean, ColBERT, and Qwen 2.5 72B LLM. But before we proceed, I create weekly tutorials and guides on large language models, so subscribe if you want to keep up with the current state of stacks and models in LLMs. Let's talk about the hero of this video. What are RAGs? Retrieval-Augmented Generation systems significantly advance the capabilities of LLMs. RAGs integrate traditional information retrieval mechanisms with generative models, enabling them to fetch relevant external information in real time before crafting responses. This approach addresses a critical limitation of standalone LLMs, which rely solely on their training data and can need help with accuracy, especially for niche or specialized topics. By leveraging real time data retrieval, RAG systems can provide more contextually accurate and up to date answers, enhancing their utility across various applications from customer support to content generation. Now, I for one understand the RAG exhaustion in the market with every second influencer and blogger or newsletter talking about the damn topic, but never really explaining how to achieve it. So, that finally brings us to our tutorial. We will cover several key objectives. If you wish to replicate the results, the GitHub link holding the repository should be found down in the description. So, for the task, we have chosen to go with the HotPotQA dataset, a dataset designed to evaluate machine comprehension in multi-hop QA tasks. Unlike traditional QA datasets that typically focus on single document questions, HotPotQA presents a unique challenge by requiring models to perform reasoning across multiple documents to derive answers. Each question in the dataset is associated with several context passages. The model must identify and integrate information from these disparate sources to achieve the correct response. This makes it particularly useful for assessing a model's ability to engage in complex reasoning and inference across multiple files. For the more inquisitive, I'll be sharing how one can go about generating data for retrieval in my following videos. So, this is how we will be adding the dataset for contextual retrieval in the pipeline. Moving on to our retrieval model of choice, ColBERT V2 is a neural network model explicitly designed for information retrieval. It builds upon the original BERT paper by integrating contextualized embeddings to improve data understanding and enhance retrieval performance. The model's dual encoder approach, which lets it encode both query and documents in a shared space, allows for a more effective matching and retrieval from the dataset based on semantic similarities. The model, since its conception, has shifted its weight and most of its functionality to DSPy, which is what we will be using for most of our implementation going forward. We will also be loading the abstract available in the model for Wiki 17 dataset, which is a collection of various information from Wikipedia pages. For the generative model, we'll be using Qwen's latest LLM, Qwen 2.5 72B. Alibaba released this 72 billion parameter model earlier this month with its high-level vision language models. We are bringing this model from the free deployed instance from Qwen Studio. This is where we start introducing more complex code in our pipeline. We will declare a custom language model class for DSPy, enabling us to import our model from Qwen Studio. We will explicitly initialize cogs in this class, which should let DSPy communicate with our model without any hindrance or unwanted warnings regarding the input stream of our model, and carry forward the model parameters in a more understandable way for the future. Finally, we can initialize the DSPy workflow for setting Qwen model as a language model that will be used for generation and ColBERT for retrieval model. Now, moving on to the RAG implementation, we will be declaring a class called simplified Boolean. This class is derived from the original Boolean method for multi-hop reasoning introduced back in 2021. It has three major functions except the init function. Generate query, which is a function that combines context retrieved over multiple hops with the actual user query to pass forward to our generator model. Generate answer is a function that explicitly asks the generator to refer to context to answer the user's query. Finally, the forward function retrieves information from the data to systematically add it to an empty context array which will further help generate answer function come up with an contextually accurate answer. As far as the final output from the model is concerned, we'll be passing a query to the RAG instance which should use all the functions that we defined above to generate context and answer a query based on that. The model output should look something like this, which clearly tells us the context it retrieved from the inference and the final output. I hope the tutorial was helpful to you. If you would like to watch us very specific tutorials around LLMs or VLMs, let me know down in the comments. Until then, keep your models fed and your code bug free.